Thanks for having me here. It's a pleasure, as we were discussing before, to have the chance to have this remote meeting even during this dreadful epidemic. So at least there are some small positive outcomes of this. So we can, as academia, we can still cluster together across distances. So today we'll take the chance to tell you about a few lines of research around the quest for detecting filaments of the cosmic web, both through their thermal and their non-thermal signatures. This is work done by many people, even many more than are listed here. These are the ones that mostly contributed to the material I'm going to present you today, but I will tell you a bit more about my group later on. And I will just start. So if there are any pressing questions, something I'm not explaining well and it's fundamental for you to understand, just please interrupt me at any time. I will try to make it understandable for a wider audience. So let's begin with a list of questions. Why do we care of image and detect the cosmic web? So the first big question, maybe possibly the one you are most familiar with is the hunt for missing baryons. So the problem is that we know how many baryons have been produced and should be in the universe because we can now more or less count them on the CMB. We know they are there at redshift 1000, so soon after the start of this universe, so to say. And then we would like to be able to count them through different observational proxies at different redshift. And if you use, for example, the Lyman alpha forest, we can reasonably well match this cosmic baryon budget. But as we approach the redshift range from 2 until today, redshift 0, we start being unable to close this pie of the baryons in the universe. This is, for example, a recent not so recent compilation of the baryons you can detect through different observational approaches in different gas phases, and still about 30 or even 50% of those baryons seems to be missing. It's a tricky business because you are using very different proxies. You can use galaxies, intracluster medium, photoionized Lyman alpha forest. You can use different emission or absorption lines. Sometimes you are double counting the same tracers. You are associating them with, you are double counting the amount of baryons that maybe different elements are tracing, but still the consensus is that if we go to redshift below redshift 2, we are falling short of 30 to 50% of baryons that should be there because they were there at the epoch of the CMB. In the last few years, several claims of detections have been reported. So the picture supported by cosmological simulations mainly is that the baryons we cannot see now are now locked in the filamentary component of the cosmic web in a range of density and temperature that makes them very difficult for us to observe because they don't emit much. They are in low density environment. They are just difficult to observe. This is a very sketchy compilation of some of the latest claims of detection or imaging. We go from, for example, direct imaging of filaments connected to this famous galaxy cluster observed by with XMM. This might be the ending part of filaments. We have the claim of detection of an absorption feature connected to the cosmic web absorbing as redshift 0.4. We have the claim of detection of the stacked signal from many filaments connecting pairs of either galaxies or galaxy clusters here. Or we also have the claim of detection of another filament on smaller scale at closer redshift. Whatever you do, if you're able to detect or to claim a detection of the missing baryons of the cosmic web, you are almost for sure going into nature and science. But so far, this is repeated several times because no one is exactly sure of the detection until probably we can get really the picture of the cosmic web into its entirety. I will come back again to this problem later. Other point, why do we care? One point I'm now really passionate about is that actually, unlike what we would expect, the dynamics, especially of gas ending up into the cosmic web, so in filaments connecting structure of the cosmic web, is much more complicated and difficult to predict than what we would naively expect. One would expect, okay, halos are complex because they have a lot of ongoing accretions, but filaments are just almost non-linear, mildly non-linear structure. They should be just slowly compressing their gas. Nothing fancy should be happening there. Actually, this is not what you see in simulation if you closely look at them. This is, for example, one of our simulations showing the formation of halos and the accretion through filaments. And you have on the left the gas density evolution in 3D. This is just a simulation, of course, and you might get the idea, okay, the gas will be just compressing and most of the action is actually taking place within halos. On the right, you have instead the same movie showing the evolution of gas entropy, and red means hot gas and high entropy, and blue means low entropy. So you have these fantastic and very spectacular shock waves that are sweeping and through the material and going actually outside, away from filaments. And when they intersect each other, they inject turbulence, they can accelerate particles, they can amplify magnetic fields. They are very difficult to observe. They tend to travel very far away and from the spine of filaments, and they also tend to define actually the boundary between the smooth universe and the collapsing universe. But if you can just look at their pattern and study their dynamics, they are not very simple at all. Also because every one of such perturbation is usually a strong shocks, meaning Mach number much larger than 1, can be also 100, and a single of these shocks can randomly entirely change the order of magnitude of the thermal, magnetic, kinetic energy of the gas they are sweeping through. So they are single events able to entirely recycle the information that was at some point in the gas surrounding filaments. And this is not what's usually happening in galaxy clustering, which are more stable objects in the sense that you need very strong perturbation to change their thermodynamics. Early this year, I was presenting this extravaganza, if you want to call it. I was trying to analyze the result of simple simulations using tools from information theory that allows me to simulate, to measure exactly how much complex is the evolution of single cells in the simulation. So I can measure exactly complexity in bits per cell. So it's not something qualitative, you can really measure this quantity. How can I measure that? Essentially, you can read the paper if you like, but basically you can use the simulation to measure how many bits of information did the code need to evolve the state of a particular cell. And you can study if you need more information to evolve, for example, the center of a galaxy cluster like here, a void like here, or a filament. And on average, what you find is that, for example, you can study how energy beams, which are centered, for example, in the typical thermal energy beam of filaments, voids, or halos, would evolve with time. If they evolve and their energy is changing across many, many orders of magnitude, it means that basically you have to have more information available to you, more bits of information available to you or to your code to predict their evolution, because they can move in energy levels a lot. If you are in a void, for example, like here, you can expect that on average, you will still be in a void even at the next time step, because you are in a very boring region, there are no perturbation reaching you, you just need a few bits of information. If you are in a halo, most of the time, you will still try to be close to hydrostatic equilibrium once your halo has formed, and only if you have so-called major merger, your energy will change a lot. If you are instead in these intermediate regions of matter sheets or filaments, which are marked here by orange colors, you are at the boundary between what is smooth and what is collapsing, which means you are very often subject to strong perturbation, and this can recycle your energy and make the predictions of your next step in evolution difficult to obtain. The physics is simple. We are still speaking at this level of hydrodynamics, shock waves, but predicting exactly how much you are going to evolve require, for example, to know all the neighborhood of your cells. You need to, for example, work out shock jump condition. You need to essentially be aware of what's coming towards you. And in that case, this is mirrored by the fact that the probability distribution of where your energy level is going to be is spreading over time. And you can use that as in information theory to build really a 3D matrix of bits per cell that are required to evolve that part of the computation. And this is just a three-dimensional dive into the simulation at redshift 0. You can see the most complex regions on average are the ones that are surrounding filaments or galaxy clusters. The physics, let me repeat, the physics behind it is very simple. It's deterministic. We know what's the physics there. But even for the code to evolve what's going to happen in that particular cell, if you are in these boundary regions, you need, for example, to update your shock jump condition. You need to know if the medium is going to develop a shock, or which Mach number, in which direction, etc., etc. So this turns into an estimate of high complexity in an information sense for those regions. The third part, which is what actually my research group is all about, is to understand the origin of cosmic magnetism. So let me take an aside. So if we try to sketch here on this plot what we know about the typical magnetization of the universe as a function of cosmic overdensity, and we have voids, filaments, galaxy cluster, and galaxy here, we can now, I mean, we know since decades the magnetic fields in galaxies is of the order of tens of microgauss with some profile, with some distribution, but we can measure it very well, and now with new radio telescopes we can measure it almost trivially in a sense. For galaxy clusters, we have evidence of magnetic fields of the order of a few microgauss in their center, and if they are perturbed, for very few clusters, we can now also measure the drop of the magnetic field profile, and actually only in the coma cluster, we have this information using Faraday rotation information up to the virial radius almost. So we have evidence is not super strong because it's just for one or very few other objects. In that case, we do see a drop of magnetic field to the sub-microgauss level. Then we have no clue basically for orders of magnitude in overdensity. We have super big upper and lower limits, and then we have to use the limits from the analysis of the cosmic microwave background to limit the amplitude of primordial fields, and now the limits are of the order of 2 nanogauss. And if we believe those magnetic fields would just evolve in the voids following basically passive and simple MHD, we can turn this limit also in a limit of 2 or a few nanogauss in the nowadays magnetization of voids. Then we have lower limits somewhere here that are deriving from the non-detection of some high energy electromagnetic cascades around distant blazar, but basically we have an enormous region in overdensity in which we have no clue about the amplitude of magnetic fields. And if we turn all this into an estimate on how much do we know of magnetic fields in the universe in terms of volume, most of the volume is going to be filled by this part. And we have that roughly, we have no clue about the magnetization properties of 99.99% of the cosmic volume. We have super wide upper and lower limits. We don't have an estimate of the amplitude and even of the topology of magnetic fields. There are two possible origin scenarios to explain the magnetization that we observe in compact structures, and we can have either an astrophysical origin in which we imagine the magnetic fields we do see nowadays are the result of low redshift, meaning below redshift 6 or 10, release of magnetic fields from compact objects that would release currents and then amplify them during structural formation. So we are speaking of jets from radio galaxies, for example, or AGNs or supernovae. On the other hand, we can have primordial mechanism in which the magnetic fields were created essentially in a very early universe through high energy processes or during baryogenesis or inflation. So they are almost present everywhere in the universe and are just compressed and being amplified somewhere. So in the right scenario, we would expect to have some remnant of magnetization almost everywhere in the universe. Nature can decide actually to use both, of course, and the hope is that with the next generation of radio telescope, I think you know well, the SKA and all its precursors, the hopes are that we can either detect the origin of cosmic magnetic fields or at least start really killing theories, because we can now use a radio telescope as a probe of cosmic magnetization in low density environments in the universe. This is how the two scenarios would look like. So now we can simulate different scenarios on board on the same set of cosmological initial conditions. So here we have in the two panels is the same simulation as the same dark matter structure, same structures, but it's run twice. On the left, I only use primordial seeding. So I just initialize the magnetic field at the beginning uniformly everywhere, compatible with CMB limits. And on the right, I'm just seeding it through galaxy formation related processes. And that's what you see. So magnetic fields from, for example, star formation would only start existing at low redshift, and they would pollute the medium around their halos. And at some point, the magnetization can drop to almost zero or can be extremely low. And you have really these two, if you move away from halos, you can predict very different trends in topology, strength, etc. This is, for example, a recent surveys we did. Again, same simulation. Actually, the full simulation has 24 different magnetization models. These are the most plausible, and you can go from different extremes of having something very volume filling, in which also the filaments are extremely well magnetized at the level of fraction of a microgauss, or they can be almost unmagnetized if they don't have an halo within them, I mean, close to them. And the key point is that if we go to this environment, and especially filaments are the sweet spot to look for this effect, we can expect to see memory of the seeding events, because filaments on one end are evolving in a complex way, but on the other, their complexity is not recycling the magnetic field. We don't have really the sustained turbulence we expect to have in galaxy cluster or in galaxies, for example. So the magnetic fields we see there can be compressed, but is never the result of a dynamo amplification that would otherwise erase the dynamical memory of the seeding event. So if we can get a signal from filaments, I mean, statistics of filaments, there are hopes that that signal is really related with some simple transformation to the amplitude of seed fields. So if we don't detect a signal in radio at all, we might expect that the origin scenarios of the magnetic field we see in halos is coming, for example, from astrophysical scenarios related to galaxy formation, or vice versa. If we find evidence of magnetic fields in filaments far away from galaxies, we can think it must be something primordial, because no galaxy formation scenario based on our simulation and the one of other groups would be able to pollute filaments on very big scales. For example, you can now, with these different models, produce a scaling relation of filaments. So this would be the total mass, baryonic mass of filaments and their average magnetization. And you can ask a radio observation of the future of tell you which is the universe you are living in. So the point now, if we are connecting these different topics, the quest of finding filaments is interesting both for the hunt for missing baryons and for the hunt of the origin of magnetic fields. And curiously enough, on one end you have the cosmic baryons. We know were there, say, at the epoch of the CMB, and somehow got lost below redshift 2. On the other end, magnetic fields, we observe them more or less until redshift 2, actually redshift 6 in some radio galaxies, but we don't know if they were there at redshift 1000. And filaments, which are only mildly nonlinear structure in the universe, are more or less at the crossroad of these different trends, and are the places in which now we would like to have information on both open questions. So if we detect them, we will learn automatically a lot about missing baryons and origin of magnetic fields. Just a few words now. I put almost no detail on numerical simulation. Let me just mention that everything I'm going to show you has been obtained here using the endocosmological code, which is a code mostly developed in the United States through a collaboration of many different institutes. I'm not a code developer, I'm just a user, and I put on the code over the years some modifications of mine and my group. Basically, it's evolving dark matter, assuming it's a collisional fluid of particles. Everything we simulate here is using a standard lambda CDM cosmology with some set of recent parameters, cosmological parameters. All this is coupled with ideal MHD equation in a co-moving frame. So we have magnetic field evolution. We need to have either, I mean, for basically the induction equation here to work, we need either to have a seed field at the beginning, or we need to have an impulsive injection of magnetic field from, for example, galaxy formation. If we start from zero magnetic field, this equation will give us also zero magnetic field at the end. So we need to guess the seed somehow. And this is all working on an Eulerian base, can be either a static mesh or a refining mesh, and you are always trying to reconstruct your problem through, you're modeling basically the discontinuities you see between cells and try to understand if those discontinuities are going to lead to a shock, a rarefaction wave, a compression, and so forth. And the other word is about my group. So everything I'm going to present here is the result of the work of all these people, mostly. And this is a group founded by the European Union through a starting grant started in 2017. And we try to cover as much as possible, combining new observations and new simulation, all these different topics that goes from, again, the origin of magnetic field, how do magnetic fields look like in galaxy cluster, can we detect them on large structure. This is, as I'm going to show you, is pretty much coupled with the issue also of understanding how are radio emitting particles accelerated by, for example, shocks in the universe. We can use Faraday rotation. We can also use fast radio burst. I won't have time to cover all the production of the group so far, but if you want, you can just go to the website and we are listing all papers there. Yeah, the MECCOW acronym, the magnetized cosmic web, I actually hate it, but it's there in the proposal, so now you have to live with the cow here. Okay, let's start now with more recent results, and let's try to combine now the challenge of detecting the cosmic web through X-ray and through radio emission. This is one of our, this is the largest MHD cosmological simulation ever in the literature so far. It has a 2,400 cubic cells. Those cells are static. It's a 100 megaparsec, so we achieve a 40 kiloparsec fixed resolution everywhere, which is not enough to properly resolve galaxy formation processes, but is very good to resolve, for example, accretion properties of filaments or properties of voids, etc. And it took some 2 million hours on a supercluster in Switzerland. Basically, this is also the same amount of dark matter particles, and there are basically twice as many dark matter particles in the simulation as inhabitants on planet Earth. So you can give really the name and surname of every person on the Earth, and you can use all particles in the simulation just to do that. What you see here is at the redshift 0 X-ray emission. I will give you a bit more detail of that, but just to give you the idea that X-ray emission is basically a strong function of density, is density square and temperature to the square root for simplicity, plus you have emission lines, and is pretty much correlating with density enhancement. So you see all these bubbles are galaxy groups or galaxy clusters. We are still not applying any observational cut to it. The green line, the grid colors are for the magnetic fields that are more diffuse, distributed everywhere. They are amplified in cluster, but they also are, in this case, that's a primordial scenario. So that's the most basically optimistic scenario we have for the existence of magnetic fields. They still are in place in between filaments, in between structure. And now we want also to compute the radio emission from the same volume. So how are we going to predict the radio emission from the cosmic web, which is this sort of emission? The blue one that you see still is following somehow halos and filaments, but is much more widely distributed. You can somehow here see accretion shocks, and the emission can reach further out from the center of galaxy clusters. And the task of the work I'm shortly going to show you was to see if there were regions in which we can hope to detect, not at the same time, but in the same position in the sky, signals of the cosmic web through X-ray and radio imaging, and then combine this information to learn more about this rarefied plasma. But first I need to explain you briefly how do we illuminate the radio cosmic web. So one important point to know is the one I already mentioned once, which is structure formation does require the formation of shocks. This is known since the Zeldovich pancake model in '72, basically. But if you form halos or you form even filaments, matter at some point will accrete supersonically, so must undergo the dissipation through shocks. And those shocks can, you see, all those surfaces marked in blue, and the yellow arrow here in this recent simulation are also marking the propagation direction of shocks. All these shocks are basically marking the boundary between the collapsing universe and the already collapsed universe. After the matter has been shocked, it's basically break down to something which is as a smaller velocity than in full velocity, and it's hotter because you went through shock heating. So if you're looking for filaments, you are looking at some level through the shocks that is surrounding them. So if shocks would emit in radio, this would be good for our quest, right? And actually, we do know that there is a lot of radio emissions in galaxy cluster, within galaxy cluster related to shocks. There are now more than, I guess, 40 known so-called radio relics that are all these elongated radio emitting structures. And for many galaxy clusters, we know well that those emissions are related with shock waves. For example, in this cluster, we have the collision of these two cluster cores that they already cross each other, and every numerical model will tell you a cluster like this would produce shock waves here and here that are expanding. And in some cases, we could also actually measure the temperature or density jump across those shocks. And across those shocks, we also have evidence of radio emission. So the strong idea in the community since now, I guess, 2 decades is that radio relics, that sort of emission, are related to shocks somehow moving a part of their kinetic energy, of the energy dissipated at the shock, is going into the acceleration of radio emitting electrons. If you have a magnetic field, you would emit in synchrotron emission. There are still a lot of open questions. For example, we don't know exactly what is the acceleration efficiency of this process. We don't know for a given, say, 1 erg of kinetic energy, how much would be the ergs per second of emission in synchrotron, because we don't know exactly what is the efficiency of translation of kinetic energy into particle acceleration. This is one of the most spectacular known so far. It's called the toothbrush radio relic. It's almost 2 megaparsec from side to side. The center of the cluster will be somewhere down here. This is work by a postdoc in my group, Kamlesh Rajpurohit. And it's an incredible, I mean, what used to be until a few years ago in previous radio observation, simple shocks like arc-like structure with few contours, now is breaking down into a complexity of multiple threads or bristles here. So we still don't know exactly what's going to, what's happening here, why the shock structure should be so much fragmented, how this is related to the physics of the gas also, but we know shocks are there and we know they are accelerating particles at some level. And also they produce almost perfect radio spectra. You see here, this has been published last week, I guess. And this is basically the most unbroken power law in the sky you have for radio relics, more than 2 orders of magnitude. And you can really use this, the properties of this power law, for example, to infer the Mach number, the age of particles, etc. All the theory behind this is coming from basically the old Fermi one acceleration mechanism. And now the modern version, modern meaning 30 years or more, 40, is called diffusive shock acceleration. So the basic idea is the same of the Fermi mechanism. You have particles that are trapped between magnetic irregularities that are produced at the shock corrugation, at the shock front, and a very small, I mean, a decreasingly small amount of particles gets trapped and have multiple collisions. Each of these collisions can increase the energy of a particle fractionally with respect to its previous energy, and you can produce almost naturally a power law of particles that would become relativistic, starting from a Maxwellian distribution. And only a tiny fraction, we are really speaking as a number of less than 10 to the minus 4 of particles gets accelerated, but they can become relativistic and therefore they can emit radio waves if they are electron and if they are embedded into a magnetic field. And so energetically, we really need to dissipate a tiny, tiny fraction of the kinetic energy flux through shocks. And the good properties of this mechanism is that they predict, for example, that particle spectra would depend on the shock Mach number. So if you can also cross-correlate with X-ray information, you can really try to kill the theory, or actually most of the time, we are now narrowing down the Mach number of shocks in galaxy cluster for something between 2 and 4, which still is a problem, but I mean, we are speaking of a factor 2 in Mach number strength. And also the prediction is that the shock, the relic radio power, which scale as a combination of gas density, the shock velocity cubic, the magnetic field to the power of 2, if we are speaking of weak field, and if the shock is strong, it's a simple function of the frequency. So this is what we know it's happening in galaxy clusters, and in what I'm going to show you in these works, we are extrapolating the same theory for the regime of stronger shocks on larger scale to predict also what's going to happen in filaments. So there is a continuity, it's the same model. We need to extrapolate it to the regime of stronger shocks that on one end would boost the expected acceleration efficiency, because acceleration of electrons should be stronger for stronger Mach number, and the Mach number around filaments is several tens, if not 100. On the other end, we still have to have a direct proof of that. So we are still in the regime of let's say, reasonable physical extrapolation. And this is a nice 3D rendering of the network of shocks. So everything you see here is actually the synchrotron cosmic web in the same simulation I showed you before in a recent 3D rendering of Torrance Hodgson, which is a PhD student at Curtin University in Australia. So you can see red means the lot of power we see inside galaxy clusters. So this would be the analogous of the radio relics we do see in observations. And now the scale is actually going down logarithmically, and all these very tiny sharp structure we have around filaments or accretion shocks are very challenging to observe. They are several decades of energy lower than what you would expect in powerful radio relics, but they are also probing longer line of sight, because the same shock can be several megaparsec thick, and this is what we are going to use to do prediction of the synchrotron cosmic web, basically. Now, let's go back to the challenge of cross-correlating this with X-ray analysis. And we did that. This is work mostly done with Stefano Ettori as a main collaborator. We took the same sky model and we produced mock now photon images in X-ray on the left, or mock radio images on the right. And we already did that for 2 instruments. So here we want to compare, I mean, it's more or less clear we cannot have any efficient imaging nowadays on wide areas with existing instruments. So we did mostly the experiment for future instrument, meaning the Athena W5, the Athena satellite, which is an X-ray satellite, which is supposed to fly in 2031, if I'm not mistaken, which is going to produce a very wide area, like 40 prime. Here would be the area in this case, a 40 prime largest position of the sky with a wide field imager, and then it's going to have on smaller bits of 5 primes across, also spectroscopy, much better than any instrument in X-ray before, especially also after the failure of Hitomi. And on the right, we did predictions already for the SK law, even if this was the most pessimistic configuration until a few months ago. So after a so-called rebaselining, I'm not sure this is still an option, or maybe things got better to the 60 or 65 kilometers, but let's say we tried already from the most pessimistic configuration. So one important thing to notice is that on the left, you would see the photons that you would get from the sky in X-ray in this particular energy band, even if Athena is a larger one, but this is the one giving the better result for the cosmic web. This is what you would be observing if you can tessellate the entire sky with a 1 megasecond exposure everywhere with the instrument, which you won't be able to do. So this is something that gives you the idea of what should be there, but then you need to decide what is the right spot to invest this megasecond observation. On the right, this is instead what the SK law is supposed really to see in its survey. So it's going to cover all this amount of the sky. This is not a full sky, but it's a large chunk of the sky. This would be a 5 degrees times 5 degree field of view of SK law. So the challenge was here in simulation to understand, are there places in which we have at the same time available X-ray photons to do thermodynamical study and available radio photons to do study of synchrotron and magnetic field. And we already applied, say, sky background or galactic absorption for the Milky Way, for the X-ray observations, or thermal and confusion noise and UV sampling for radio observation. So it's simplified, but we try to include all the possible reason of confusion or troubles in both observations. So this is what you would get if you can observe hypothetically the entire sky. This is what you get if you remove all halos in the two images. So you can see by yourself that a very, very little is left. So somehow here we have some residual emission in between, say, probably two halos. Also here you see when we have chain of galaxy cluster, we tend to see a small excess of radio signal. Here we tend to see sometimes some like circular excess of X-ray and maybe something here, but it's very hard to see. So the problem is that in X-ray, after we remove the hot and dense gas, everything very soon goes away from the visible X-ray window. Those particles just don't emit X-ray photons anymore. We can quantify. This would be for the same two sky models. We have here the distribution of their intensity of emission in X-ray, and here in radio, and here we are applying observational cuts. So Athena, even in 1 megasecond, would observe everything which is at the right of this line, and the SK law would observe everything which is on top of this line. And we can, in the simulation, identify which pixels belong to cluster outskirts, to filaments. So the clear message is that in X-ray, you would detect with Athena, provided you can tessellate the sky with 1 megasecond everywhere, which you won't do, but in principle, that tells you the sensitivity of the instrument. You will detect everything from clusters and groups until they are 200 radius, more or less. A very, very little of cluster outskirts, almost no filaments at all. On the other end, in radio, you would detect a lot from galaxy clusters and group. In our model, let's remind, we only see the radio signal if there are shocks. We are neglecting radio galaxies, radio halos. So that's why we don't observe all clusters, all groups. We need a shock in those systems to be strong enough to be detectable. But okay, in the real radio universe, there will be more from galaxy clusters and galaxy groups. We would be able to observe some cluster outskirts and the tip of the iceberg of the distribution of filaments. And we can even do statistics, and the only regime in which you would have detection, both with Athena and SK law on a statistical level, it's, I mean, beside galaxy cluster, but this is not our task here, you need to go to cluster outskirts. So extreme periphery of galaxy cluster, but there is little to no hope of having a joint detection of radio and X-ray from filaments in the empty universe. Like filaments connecting galaxy cluster on very large distances are almost unobservable in this model. So what are those clusters? Okay, in the paper, this is a paper from last year. Actually, we also tested, Rosita was still going to be launched, XMM, you can get an idea what is the best energy range to detect gas with some temperature as a function of exposure, for example, but okay, you can look at the paper if you're interested. And this is what you would, again, detect if you compare the two approaches. So in X-ray, you would be able to detect, this is again a phase diagram. Now we are plotting the density and temperature projected of the sky model. And we are, this is where the baryons in the simulation are. So your missing baryons would mostly be in this phase, the low temperature, intermediate density range, say. And this is how much of this you're going to detect, for example, in X-ray with this 1 megasecond, most optimistic, I mean, absurdly optimistic Athena exposure. You will detect basically 100% of photons that are coming from this phase, which is the one of galaxy clusters. But unluckily, you will only scratch the surface of the missing baryon part if you use X-ray, because the emission would go down rapidly as density squared, and also the temperature is becoming too cold for the gas to emit an X-ray. On the other hand, in radio, you start probing a larger chunk, you see, of this phase. So in principle, you can detect and illuminate the cosmic web and the missing baryons that are locked there through their magnetic effect. So the magnetic fields are not such a strong function of density, and if they are there, they would illuminate the missing baryons if they are shocked, even if their density is not so high. So in principle, it makes sense to look for the cosmic web using the radio signature. Speaking of what is actually should be possible to detect using both wavelengths, let me check the time. Okay, we found that in the simulation, those cluster outskirts I was meaning are all these blue basically patches. Some of those are coming from within galaxy cluster, but there are some residual blue patches that are regions in principle that we can detect both using X-ray and radio with the specifications we adopted for this study, and they are mostly related to cluster-cluster bridges. So we analyzed systematically all pair of clusters in the simulation and found that most of these double detections are coming from short connections between galaxy clusters. I wouldn't call that filaments, because at the time in which we have these both double detections, either in radio, all these instruments here, or in X-ray here for different instruments, those filaments are so squeezed and they are so short that basically they are almost engulfed between the virial radii of clusters. Not entirely, but close to it. So they are not the isolated filament we need to detect to, for example, learn about the origin of magnetic fields. But in that case, if we select those objects from 5 to 20% of the area connecting them, this will be a profile, and this will be the detectable fraction of the area connected cluster 1 to cluster 2 that you will be able to detect using all these instruments and all these exposure. And if you do proper cuts in mass or projected separation, you can boost this to several, I don't know, yeah, you can reach 30, 40%, something like that. So this is good. So it gives us a class of candidates that we can use for an early detection of some sort of filaments and gas well outside of the virial radius of galaxy clusters. We also show that if one is sure that it makes sense to invest a 1 megasecond integration with XIFO, which is the spectroscopic unit on board of Athena, in this part, which is the bridge connecting these two clusters, you can also get enough photons to do really kinematic statistics. You can really study the Doppler effect of the gas here. So this merger is happening on a 45-degree along the line of sight. So you will be able to see some Doppler effect of the gas moving to you as an angle of 45 degrees. And you can actually study turbulence in these intercluster bridges. And we did test putting, I mean, we know what was the input value of, for example, turbulent velocity, metallicity, etc. in the simulation. And if you can have a 1 megasecond with XIFO, you can really be able to extract back this information, meaning in principle, you will be able to study the thermodynamics of gas outside of the virial radius of galaxy cluster if they are in such peculiar condition. And for example, you can also do a kinematic estimate of the Mach number, which is so far impossible in galaxy cluster. So is this really the WIM? Are those really the missing baryons? I'm still uncertain. This would be one of such systems. So this would be the gas bridge in between, and you can see a temperature map. So what is happening is that the gas in between these two systems is actually being squeezed. It used to be WIM, so warm, hot, intergalactic medium. very difficult to observe, say, 1 gigayear before the collision, but now is in this phase of being squeezed and compressed. And this has the effect of, for example, of boosting its total emission, because you are at the same time compressing the gas density and moving, I mean, and enhancing the temperature, so the gas would move inside your observational X-ray window. It's not really the WIM anymore, because the temperature in that case can reach several 10 to the 7, and the parameters would be more like intracluster medium-like, but it used to be, according to simulation, warm hot intergalactic medium. So for example, its metallicity should still be the same it used to be before the merger. So and the magnetic field, we are still uncertain. So some properties might become visible because of this effect, but maybe are still pristine and still giving you information of what used to be the system before the merger. Several claims of detection have been reported for similar system after or during this paper. This is also a very famous recent first light of Rosita, even if there is no paper so far, of this famous pair of cluster. And if you collect here the typical values of temperature and density of all claimed detections, some of those I was reviewing before, speaking of, for example, direct imaging of X-ray in filaments connecting to a cluster, of stacking of filaments in between galaxy or galaxy cluster pairs, this is the range of value you are getting. So most of direct detections here would give you the information of something which is really intracluster medium-like. It's not the regular WIM, as extreme temperature and density values, which is understood because those are rare objects that are biased to be observable with X-ray. They do not represent the regular WIM. On the other hand, what you can detect with stacking technique is more folding into the regime of the WIM we do expect to see in simulations. You don't have a direct imaging, so now you have to do population study to understand which properties you can get to the stacking technique. There are other groups doing stacking radio, so it's more complicated and you have statistics involved, but this is to tell you that all these different detection would give you something which is really, really different, separated by the few orders of magnitude in temperature and density. So coming back to the radio window, very interesting. Last year we published, and the first author is Federica Govoni from the observatory in Cagliari, in Italy, in Sardinia, the detection of the largest radio structure in the sky so far, which is the cluster-cluster bridge between these two galaxy clusters, which has been detected with LOFAR. So LOFAR detected this very long blue, in this case, structure, which is connecting the two clusters across a distance of 3 megaparsec and more. The two clusters were known to have already a radio halo, but this structure has been discovered by LOFAR. It's 3 megaparsec from side to side, and allegedly has a spectrum which is steeper than 1.3, so it's kind of steep for these sort of sources. And this couple of clusters was famous because it was the one giving the highest signal to noise, I guess, in the Planck catalog. So we know there is gas there, and modeling by several groups have shown that the gas here is very hot, as 6 Kelvin as an average temperature, and density is intracluster medium-like, more or less. Now we also know that there is radio on board of this structure. And the task for theorists or numerical simulators like myself is to understand why. So in the science paper attached to this is only the LOFAR image, okay? In the science paper attached to this article, we propose a shock acceleration scenario, the same we were using before. The problem is that if we just use shocks that are extracting energy from the thermal pool, we are unable to illuminate in radio contours, in this case, the same distance as in the observation. This is the analogous simulation of the system. We can produce rather well the SZ distribution. We cannot reproduce the radio distribution using the simple shock acceleration theory. We just need a too high efficiency. It's impossible. We can, on the other hand, surmise that there are fossil relativistic electrons that we know are there within galaxy cluster. We are not sure if there should also be in the regions connecting these two objects, but this region is so dense and so evolved that maybe there are fossil relativistic electrons. In that case, we do have shocks there. They are not powerful enough to illuminate the regions using direct shock acceleration. But if there are fossil electrons, the same weak shocks, and I'm speaking in that case of a 2.5 or 3 or 4 Mach number shocks, those shocks can just reaccelerate particles that are already there, are relativistic, were not relativistic enough to emit in synchrotron, but they get to be relativistic enough, so Lorentz factor 10 to the 4 again, in case there is a network of shocks connecting the two clusters. This was not crazy, it was reasonable, but required some fine tuning. For example, you need to have a fine tuning for the filling factor of shocks and for the age of these fossil electrons. If you get some of these numbers wrong, even by a factor of 2, you will get inconsistent particle spectra. You would expect to see, for example, a lot of inverse Compton emission, which is undetected. So it was reasonable, but it requires some fine tuning. Later this year, we propose another scenario. In this case, the first author is Franco Brunetti, and here we involve instead turbulence. So this region is being compressed, and at the same time, you have you have gas flows converging to the joint between the two clusters, and this is injecting turbulence of the solenoidal kind. So you are injecting vorticity. You just need to dissipate a tiny, tiny, tiny fraction of this kinetic energy to explain the radio emission. And Gianfranco Brunetti, who's an expert on radio halos and acceleration in the center of galaxy cluster, worked out another recipe, which is, a theory, but seems to make sense in that case. You are using the same energy that the gas is using to amplify the magnetic field to the dynamo effect. You are also using the same energy to accelerate particles. And in that case, you can explain the emergence of radio emission from side to side of this cluster, because there is a lot of free energy that you can use. You cannot use the free energy from shocks because there are not enough in that case, but in that system, you have a lot of solenoidal kinetic energy. And this is what you would see in that case. So you would see the radio emission here, it's only from radio halos, but at some point, when the two clusters have the right distance, automatically they will produce, like here, a lot of solenoidal, so vertical turbulence. They would boost the magnetic field, and the same process amplify the magnetic field, is also trapping particles in another sort of Fermi acceleration. And you would start to produce bridge that in this case are short-lived. You need really to weigh the cluster to be closer than a certain distance. And this phase would just basically be anticipating the later merger of the two clusters. So the other prediction is that you would expect also to find pre-merger emission with steep spectra in between the two. Okay, and there are some strong prediction in that case of this model that actually is alleviating some of the fine-tuning problem we were requiring before. You also have, of course, prediction you want to test. And one, for example, is that in this mechanism, you would expect to see only very localized emission structures at high frequency and very diffuse and smooth emission at low frequency. So it's not the same structure at all frequencies, but you really change the morphology, for example. Now, I'm falling short. So let me just review a few other lines of research. So I presented the quest for the cosmic web using synchrotron emission. You can also use, hopefully, Faraday rotation. So you can take advantage of the fact that the polarized emission from background sources, if it's shining through a magnetized medium, as its direction of polarization rotated as a function of the gas density and the magnetic field along the line of sight. If the signal is large enough for your radio telescope to observe it, you can understand how big is the magnetic field along the line of sight and decide if it's, for example, the effect of a rotation from a primordial scenario in the left. We are looking at the the Faraday rotation for a uniform background of sources in the backyard of a, in the background of a galaxy cluster whose magnetic field is being produced by a primordial model, or instead where magnetic fields are only being produced for AGN. And you can detect clearly, you would expect different scenarios. You can compute statistics and find that if magnetic fields are coming from a primordial scenario, which is very volume filling, you expect to see some Faraday rotation everywhere around structure, and instead you have at least a decade less of Faraday rotation if the signal is coming from an astrophysical scenario. And in this paper by a PhD in my group, with these statistics for an instrument that could be Meerkat, actually, showing that if you don't have the annoying contamination from actually the Faraday rotation intrinsic to the source, so also the radio galaxy that would emit Faraday polarized emission, also its own Faraday rotation, you would be able to detect like 50% of filaments connected to very large galaxy cluster if you have a Faraday rotation grid around the cluster. If you are including instead the contamination from the uncertainty arising from the intrinsic Faraday rotation from the source that would sum up to the effect of the intergalactic medium in between, you need to really detect a lot of sources from the same object to be sure that you are really detecting something from the cosmic web. This would be a challenge for any future radio survey using the Faraday rotation effect. You have contamination from the Milky Way and from what is coming intrinsic to the sources, which is at the same level of the cosmic web. Also, recently we presented a systematic study of the cross-correlation between many different observables. So we simulated for the same volume X-ray, Sunay-Zeldovich effect, neutral hydrogen, Faraday rotation, synchrotron emission, and projected distribution of galaxies, and we try to cross-correlate them to see if some of this cross-correlation gives the highest detection chances. And in short, we found that basically you always have the highest chance of detecting the gas in the cosmic web if you're using the Sunyaev-Zeldovich decrement, because this is not scaling as fast as the X-ray with density. And if you want to detect it with radio, well, you can look at the paper. There are all possible boring, I would say, combination, but basically if you use the SZ, you always have the highest chances of finding a statistical signal. And we're also trying to repeat a recent experiment by Tessa Bertram and collaborators using MWA. They claim basically an upper limit on the cross-correlation between the distribution of galaxies and the synchrotron emission around galaxies using MWA. We try to repeat the same experiment for possible different magnetization scenarios. And basically we concluded that to be compatible with the limits that are excluded, this would be a cross-correlation as a function of angular distance. This part is discarded because Wernstrom and collaborator didn't observe it using MWA. In our case, thanks to simulation, we can turn this non-detection actually in a limit on primordial magnetic fields, 0.2 nanogauss, based on this non-detection. While if magnetic fields are coming from AGNs or galaxies, we would have a cross-correlation. We would be within the bounds of the experiment with MWA. And we did something, I'm nearly done. We did something similar using the Faraday rotation effect. Also, Shane O'Sullivan recently had a paper using LOFAR, and you can compute what is the dispersion of the difference on Faraday rotation across extended sources that can either be physically associated or can be randomly associated, like two radio galaxies at a very different redshift. You can expect that random pairs of radio galaxies would have a higher Faraday rotation difference in between them because they have a different column of intergalactic medium along the line of sight, and the amplitude of this difference should be able to tell you how big is the Faraday rotation produced by the cosmic web. We could replicate the same experiment with the same set of simulation, and curiously enough, we find similar bounds of the previous experiment with NWA, which only involved the synchrotron emission, in which case we found that we can explain the limits found by O'Sullivan and collaborators using LOFAR if the primordial seed fields are below the 0.5 nanogauss level, or if magnetic fields are only a product of galaxies or AGN. Okay, I will skip over this, which is still, okay, this is going to be submitted soon. And so I'm here to my conclusion. I hope I sort of convince you that the cosmic web, especially the gas and magnetic fields in the cosmic web altogether, are a dynamic environment in which you would expect drastic changes, and the energetics of those baryons or those magnetic fields can change and be recycled continuously, iteration after iteration. So it's not as simple as we would at first sight expect. Magnetic fields seems to give us maybe the better chance of imaging, not statistically detecting, but directly imaging the missing baryons around the cosmic web for a certain set of model parameters, of scenarios for the origin of magnetic fields. And at the moment, already combining simulations and available observation, radio observation seems to be able to limit the origin of cosmic magnetism, and in particular the amplitude of primordial magnetic fields to be below, say, 0.2 nanogauss at redshift 1000. If you are interested, also today I posted a paper which is only submitted, not still have to go through a reviewing process, studying more variation of primordial mechanisms for the magnetization of large-scale structures. Okay, and that concludes my talk. I hope you enjoyed it, and now I am up for questions.
Thank you. That was really interesting. We can take a few questions now. Okay, NJ, go ahead.
Hey, I actually have 12 questions, okay, but I guess, okay, we can chat after that maybe. So let's go ahead with the student and then,
yeah.
Okay, so yeah, one of this is the following. You have shown the there's an interesting plot at relatively earlier stage that you have shown that there are magnetic fields basically generated at early universe, and then therefore CMB is able to measure it. And certainly on the small scale, on the late time, and also within the cluster and surrounding cluster, that's all what we're talking about today mostly. And there is magnetic field. And I understand what you are analyzing that as a density environment. But can you, or let's say, is there any clue of how that magnetic field initiate and then evolve over the really billions of years of cosmic time, and being enhanced in the small structures? I guess my question is about how can you plot the magnetic field as a function of time, cosmic time, in some way?
Oh yeah, sure. Yeah. That's no. One thing I would like to stress is that it still have to be proven that there is any primordial magnetic field. CMB can only give you limits. So if they can only tell you if there was a primordial magnetic field with some spectra, the paper I was mentioning today is actually all about that. Depending on the amplitude and scale distribution of any primordial magnetic field, you would expect to introduce several perturbations in the CMB because the gas would have more tension, you can have lensing effect, anisotropy, etc., etc. You can use the CMB as a prior and saying, since I don't see those sort of perturbations above a certain limit, I'm going to tell you, I'm going to constrain the amplitude of initial primordial magnetic field. But so far, there is no claim whatsoever of a detection of magnetic field. So what we can only do is to assume the maximal magnetic field, say, configuration that is allowed by CMB, and see if this is enough to reproduce the evolution of magnetic fields inside clusters, for example. And this we did already. For example, we showed a couple of years ago using simulation of high resolution that we can start with a magnetic field as small as 0.1 nanogauss co-moving, which is a factor 10 below the CMB limits, and we can get to magnetic fields which are compatible with galaxy cluster observation of the coma cluster nowadays. I must say this was not the first time. This has been already argued since 1 decade or more using other sort of simulation. In our case, we use that using grid Eulerian simulation that gives you some sort of control. But okay, many people, let me mention, Klaus Dolag from Max Planck since already 20 years have claimed that. And this would explain the magnetic field in galaxy clusters. So you have a first stage of basically, first you have a rarefaction of the magnetic field, and if you are living in a structure, you have a compression, and the compression is giving a kick to the magnetic field, and as soon as you start entering into the small scale dynamo regime, and you need to have basically a large Reynolds numbers to do that, you go through a stochastic amplification that first is exponential, then linear, and people have worked out through different approaches that this is surely doable for galaxy clusters. Or if you have a regular field plus a rotation, like in the case of galaxies, plus instabilities, etc., you can get to the field you observe nowadays. So the evolution from primordial fields, if there is any primordial field, to nowadays collapsed structure is almost no problem. It is a problem if you want to look into details, but zero level is no problem. People are still arguing whether or not you should expect an amplification of magnetic field in dynamo-like in filaments. I would argue no, but other people would say maybe yes. In which case, you should have even higher magnetic field than what I am basically finding in my simulation. But the big question is, how do you produce any primordial field in the first place? This is a strong, pressing question.
Yeah.
Because either you have the mechanism, but you cannot, I mean, if you produce it, but if it's on super small scales, it won't be good. You need primordial magnetic field with scales of at least some kiloparsec to be able to enter into the dynamo regime. Otherwise, they would basically be useless for dynamo amplification. And people are still, I mean, it's all up in the air. You are invoking first order phase transition, baryogenesis, I mean, early universe stuff, which I'm really not familiar about.
Yeah, so basically, even though we have no clear clue of that, the primordial magnetic field will generate early on before redshift 11,000, but various mechanisms can still generate them at a very small dynamo region or compression mechanism, right? So I think that is
you can have both. Actually, nature is probably using both at some level. There are regions like voids in which you can only have one, basically. Either you have zero or you have something primordial, I guess. Close to structures, probably is both. We don't know.
Okay, so Inge, before you carry on with the other questions, there are two other questions. So I think Kavi had a question. We can come back to Inge if you have time later.
Yeah, thanks for an excellent talk, Franco. Yeah, I just wanted to check with you, with these much deeper or more sensitive radio instruments like LOFA and Meerkat, etc., we're seeing a lot more kind of extended synchrotron structures. And sorry, I'm not talking about the cosmic web here, but more focusing on like galaxy clusters, which, I think you're interested in as well. So we're seeing a lot more extended emission. So compared to the simulations, what fraction of the non-thermal kind of budget in clusters, are the current observations seeing? Have we captured all of it? Because there's a lot more than the, previous generation of radio instruments.
So what the radio observations can directly give you still is of the order of a few percent, because even if 100% of the volume would be emitting, the magnetic field which is there usually is accounting for a few percent at most of the total energy. This is, parameterized to the so-called plasma beta, which is order of 50 or 100 in galaxy clusters. So in the case of the coma cluster, for example, we also have the profile, and the plasma beta tells you there is almost 1% or 2% of energy in magnetic fields compared to the gas energy. And even if all the volume is going to be filled by the relativistic electrons that are responsible for the emission, still you would also add at most another few percent, because we are using leptons. They cannot have, on the other hand, we have upper limits, because otherwise those structures would shine through inverse Compton. So I would say if you just account from magnetic fields and leptons, so electrons, you have at most a few percent. What we don't know is that how many cosmic ray protons would be there. They would unlikely not emit synchrotron, but they would emit, they could either produce secondary radio emission if they collide with the intercluster medium and release the cascade of electrons, or they can directly produce gamma ray emission. But now the Fermi satellite has consistently lowered that down again to a few percent, which is actually a problem, because theoretically it's a problem to explain why the same shock can magically at some point accelerate so many relativistic electrons, because in radio we see them even having such weak shocks without accelerating any protons. When I started my PhD, like that 2006, the theoretical picture was accelerating electrons is hard and accelerating protons is easy. And this is not what's happening in galaxy cluster. So the big dilemma is, where are the cosmic ray protons in galaxy cluster? Why they are not accelerated? And several, a few lines of interpretation of this, also connected to my group, is that actually there is shock obliquity into play. If shocks are running almost parallel to the magnetic field, you are able to accelerate protons. If shocks are running almost perpendicular to magnetic fields, they would only accelerate electrons. Since in galaxy cluster we observe a large majority of quasi-perpendicular shocks, so of the second kind, that's a sufficient enough reason to explain why we don't see the protons. So what I was saying, magnetic field and electrons, a few percent. Cosmic ray protons below a few percent. The other player, which is very important, is turbulence, which is something that should be there. Based on everything we know, we must have turbulence there. I can show you again some of the movie. Every simulation at every resolution you are producing of these systems, they always end up having something like this. So you always form continuously turbulence, you stir it, merger after merger, it's always there. And it can go from being, again, a few percent if you are in a cool core relaxed system, and these are measurements done by Itomi in X-ray. You can measure Doppler broadening of gas, or if we go to the periphery of galaxy cluster, it can be a bit more, it can be 20, 30%. This is available free kinetic energy, is not impacting so much on X-ray estimate except for the hydrostatic mass bias estimate, but it's there. So any mechanism would be able to take this energy and make it radio emitting would start to illuminate the intercluster medium. If I answer kind of your question, I would say, all the ensemble of radio emission that modern radio telescope is telling us still is compatible with a few percent at most of emission in the volume of intercluster medium can be more if you are in the proximity of a radio galaxy, for example, if you are in lobes, etc. But altogether, we are speaking of a few percent.
Okay, no, that's an excellent kind of budget that you put together. Thanks very much.
We have a question from Benny. So how does the intercluster medium depend on the density of the plasma? Can you constrain the extragalactic magnetic field from the density of the intercluster plasma?
Not sure I get the question.
You can read the chat window. That is written in the chat window.
Let me, yeah, where do I find it? I don't see the chat window.
I guess I can read it out again if you want.
Or maybe Brendan, you can. Is Brendan still online?
I'm sorry, but I don't see the chat window. I have all windows open here.
But sharing. I can just read it out again. Or if he's still around, Benny, if you want to read cons. Okay, anyway, I'm going to read it out again.
Okay.
How does the intercluster medium depend on the density of the plasma? Can you constrain the extragalactic magnetic field from the density of the intercluster plasma?
Okay, so in my language, intracluster medium and plasma are the same thing here. So most, I mean, 99 or whatever percent of the gas which we see here is all plasma, and actually all the cosmic web I'm shown is all plasma. So actually, again, 99 blah blah percent of everything that is in simulation is plasma, and the density and temperature to the first order are expected to be unrelated of how much the magnetic field is there. So we need, of course, in intercluster medium, some level of magnetic field to keep the plasma collisional on scales much shorter than the, say, Coulomb collision scales. So we know from X-ray observation that the plasma is kept collisional, effectively collisional on scales much lower, much smaller than what the Spitzer collisionality would tell you. So particles, for example, shocks will form not because particles are hitting each other, but because there are magnetic field perturbation that are producing collective effects. But I'm not sure density or temperature can be related. So we cannot, from X-ray observation of the gas alone, infer magnetic field properties, and we cannot infer the origin of such magnetic field, I would say, as far as I can tell.